Hello maths fans, Dr. Tom Crawford here at the University of Oxford, and today we are looking at bases, spanning and linear independence. The motivation for studying the basis of a vector space is it gives us a way to measure the size of the space. You might find it helpful to think of the basis vectors as the building blocks used to create everything that belongs to that space. And if we're able to count those building blocks, then this gives us a way to represent how big that space might be. So as a first example, let's consider the vector space of polynomials up to degree n. Then if we are to write out the most general possible element of this vector space, we might have something like the following. So if we say p of x, a polynomial in our vector space up to maximum degree n would have to consist of a constant term, let's call it a0, where the 0 represents x to the power 0, which is of course 1, plus a1 times x to the power 1, plus ... where the next one would be a2 x squared. And then we'd have to stop at the maximum possible power of x, which would be an lots of x to the power n. Now, given any polynomial which has a maximum degree of n, then it has to have this form where the coefficients, the a0, a1 up to an, these coefficients can of course take any value, which does include 0. But any polynomial at all that you can think of, any polynomial in x where the maximum allowed power of x is x to the n, would fit into this form for some choice of our coefficients ai. Now, since all polynomials fit into this form, they have this same structure, then there is a recurrent feature to any such polynomial. The coefficients, the a's, they're allowed to change. So as we change the a0, a1 up to an, as we change those coefficients, we get different polynomials. But they're just telling us how much of each power of x that we want to take. So the common feature of all such polynomials, the building block of all such polynomials, is going to actually be the powers of x. So we could say that a basis for this space could be the set given by x to the naught, which is of course 1, then we have x, then we have x squared, and we continue up to x to the power n. Now, before we get to the formal definition of a basis, which I will write out in just a moment, some of you may have noticed that here we're dealing with polynomials up to degree n, and here I've told you, and again we'll see shortly, this is indeed a basis of this vector space. Now, if we were to count the number of basis vectors, then we've got n minus 1 all the way down to x to the 1, and then we've got an x to the 0, which of course is 1. So we've actually, in here, we've actually got n plus 1 elements. Now, as I said at the beginning, one of our motivations of why we study the basis of a vector space is it gives a way to represent the size of that vector space, and we do that by counting the number of elements in the basis. So polynomials up to degree n, that forms a vector space, and we say that it has dimension given by n plus 1, because there are n plus 1 elements in the standard basis for that vector space. Now, I will be discussing dimensions in much more detail in the next video in the Oxford Linear Algebra series. For the remainder of this video, I will no longer talk about the size of the basis. We will be focusing now on the actual definition and how we might check whether or not a given set is indeed a basis of a specific vector space. So the formal definition of a basis is as follows. Definition. A basis of a vector space V is a linearly independent set which spans V. So in order to understand what this means, we need two further definitions. We need to know what it means for a set to be linearly independent, and we'll be looking at this shortly, and what it means for a set of vectors to span a vector space. We'll start with the definition of a spanning set. We say a set spans a vector space if anything in the vector space can be written as a linear combination of the spanning set. So we've already seen one example when we were talking about polynomials. So this is our vector space V, polynomials up to degree n. And we just went through this example and said, well, this is in fact equal to the span of 1x squared up to x to the n, because any member of this vector space, any vector in this vector space, is always a linear combination of these vectors. So let's say, i.e., any polynomial p of x, which we wrote out very generally as a0 plus a1x plus plus an x to the n. Any polynomial, which must look like this, is a linear combination of the spanning set, so of 1x up to x to the n. So again, anything in our vector space can be written as a linear combination of all of the vectors in the spanning set. If that is true, then we say that this set spans the whole vector space. Now I could also have said that our vector space V, which consists of polynomials up to degree n, I could have said this is also equal to the span of the following: 1x increasing again up to x to the n, and 2 minus x. Now the last element here, which I've just added, is clearly just a combination of the first element and the second element. I've just taken times 2 lots of that, and here times minus 1 lot of the second element. And this is actually where linear independence or linear dependence comes in. Because for this extended spanning set, and again it is still a spanning set, it's still true that any polynomial can be written as some combination of these vectors, that will still hold. However, we actually want the minimum such spanning set in order to get our basis. And one of the ways we do that is by thinking about linear dependence and linear independence. So we would say that this set here is in fact linearly dependent precisely because I can rewrite one of the elements in terms of a combination of some of the others. So here, the final element, 2 minus x, the n plus second element, the last one is 2 lots of the first minus 1 lot of the second. So this is kind of redundant because we already have any amount of these two that we want, because we're able to control these coefficients a0 and a1 to be anything. So we already have as many constant terms, as many linear terms as we want. So just having some amount of 2 minus x, it's just an extra thing we don't really need. And that is why we would say that this set is linearly dependent, because we can rewrite this element in terms of two of the others. Now, our original spanning set up here, 1 through to x to the n, this is linearly independent because it's not possible to rewrite any one of these as a linear combination of the others. We could, of course, multiply things together. If we wanted to create x to the n, you could say that's x to the n minus 1 multiplied by x. But that is a non-linear operation. We have two things being multiplied. So a linear combination means all we can do is add together multiples of each element. Now, if you think back to the vector space axioms, or if you haven't yet, check out my video looking at the vector space axioms. We in particular were interested in these kinds of operations, taking multiples of a particular vector and adding them to multiples of another vector. And that's kind of coming in again with this definition of linear combination. And we will see this pop up in the future in further videos in the Oxford Linear Algebra series once we move on to linear transformations, but now I'm really getting quite far ahead of myself. So this set is linearly independent precisely because we cannot write any of the elements as a linear combination of the other elements. Now, the way that we define this mathematically is as follows, and this gives us our second definition. So definition over here for linear independence. So we say a set, and let's call it v1 ... up to vn is linearly independent if and only if the only solution to alpha 1 v1 plus alpha 2 v2 plus ... plus alpha n vn is equal to 0. So if the only solution is for all of them, alpha 1 equals alpha 2 equals ... they all have the same value, which is 0. So just to go over that one more time, we say a set v1 to vn is linearly independent if and only if the only solution to alpha 1 v1 plus alpha 2 v2 plus ... plus alpha n vn equal to 0, if the only possible solution to this equation is when the coefficients are all 0. If that is true, we have a linearly independent set, and in fact that is actually equivalent to what I was talking about in terms of words, because, for example, if we suppose there was another solution to this problem, to this equation, where at least one of them wasn't 0. So suppose, for example, alpha I is non-zero. We don't really care what the others are. They could be 0, but let's just suppose that at least one of them isn't 0, but this equation is satisfied. Then what we can do is actually say, well, that means that alpha I times vi is equal to minus alpha 1 v1 minus ... all the way up to minus alpha I minus 1 vi minus 1 minus alpha I plus 1 vi plus 1 minus ... all the way up to the very last one, minus alpha n vn. Again, it doesn't actually matter what the value of all of these other alphas are. If we know this one is non-zero, we can rearrange the equation to get this, and then we simply just divide by alpha I. So in other words, I've been able now to express vi, the one that had the non-zero coefficient, been able to express it in terms of all of the others. So I no longer need vi in my set. It's not bringing me any new information, because if I wanted to calculate something in terms of vi, I just take this combination of all of the others. So this would be a contradiction because this would mean linearly dependent. Because we've been able to rewrite one of the vectors in terms of the others. So the formal definition of linear independence talks about this combination being equal to 0 and the fact that the only solution is when all of these are 0. And this is actually the most helpful way to compute and to check whether or not a certain set is linearly independent or linearly dependent, check whether or not this holds. But we're also seeing that this gives us a way of actually defining something to be linearly dependent, i.e. it's not linearly independent, or you can think of it by saying it's linearly dependent if and only if you have a solution to this which is not for everything to be 0. So what this all means is that if we want to try to find a basis for a vector space, we first need to find a set of vectors which span the whole vector space. So in other words, any general element, and we saw this example with our polynomials, any general element in our vector space must be able to be written as a linear combination of the elements in our spanning set. If that's possible, then this is indeed a spanning set, or we say this set spans the vector space V. So we have to check spanning, as we've got up here, and we have to check that this set is also linearly independent. So we create this combination, if we have a set V1 to Vn, create this equation and try to solve it, and if we can show the only possible solution is when the coefficients are all 0, then we indeed have a linearly independent set. If it also spans the vector space, then by our definition we have a basis. I will go through some examples in just a moment, but before I do, I recommend everyone watching to first check out ProPrep, an online resource which provides customized tutorials for students looking to improve their skills in STEM-based subjects. The linear algebra section covers everything we've discussed so far in this video, from spanning sets and linear independence to further examples of bases for famous vector spaces such as Rn and M by N matrices. There are also several exercises which give you practice in calculating bases for given vector spaces, as well as determining whether or not a given set is linearly independent or linearly dependent. Each exercise has a full solution video, so not only can you check whether you are right, you can see a step-by-step breakdown of the solution to help identify where you may have gone wrong. Sign up now using the link in the video description for a 30-day free trial of ProPrep, courtesy of Tom Rocks Maths. We'll start with some examples of spanning sets for the Cartesian plane or the xy plane R2. So, the standard basis, which I'm going to imagine most of you have seen before, perhaps without realizing that this was the basis, is going to be given by our coordinate vectors. So if we have 1, 0 in our set and our second basis vector is 0, 1, then this is our x coordinate vector. This is a unit vector in the x direction, and this is a unit vector in the y direction. And this is the standard or canonical basis for R2, the Cartesian plane. And the way to see this, that it's spanning, first of all, is to say, well, if I have a general point x, y, can I take a linear combination of my two basis vectors to get to any point x, y? And it's quite straightforward. You just take x of the first basis vector and you add that to y of the second basis vector, and x times 1 plus y times 0 gives you x, and then x times 0 is 0 plus y times 1 gives you y. So we can see that this clearly is spanning because any point xy in the plane can be reached by taking this exact linear combination of my two vectors. Now, to see that this is also linearly independent and therefore a basis, as I claimed, so this gives us spanning. Now, for linear independence, our definition told us to consider having alpha times the first one plus beta times the second one equal to 0. Now, since we're working in 2 coordinate vectors, 0 is of course the origin, 0, 0. So if we look at the first coordinate, then we get the equation alpha times 1 plus beta times 0. So we get alpha must be 0. And then in the second coordinate, in this example, we're going to get alpha times 0, which is 0, plus beta times 1 has to also be the second entry, which is 0. So we can see the only possible solution is when both alpha and beta are 0, and then we can say this therefore implies Li linearly independent. It's spanning, it's linearly independent. This is a basis, and as I said, it's the standard or canonical basis for the Cartesian plane. Now let's consider a second set of vectors. So for our second example, still thinking about the xy plane, but now suppose we had the 2 vectors of 1, 1 and minus 1, 2. Then we want to know, first of all, does this span? Is this a spanning set for the Cartesian plane? So, spanning, question mark. And as we saw before, what we need to do is find coefficients, I called them alpha and beta, such that xy is equal to some amount of the first one plus some amount of the second one. Now, I won't solve this explicitly. You can check my answer or try and solve it for yourselves, but you can do this by taking the following. If you take 2x plus y divided by 3 lots of our first vector, so that lot of 1, 1, and then you add it to y minus x divided by 3 of our second vector, minus 1, 2, then I believe this should work. So let's just double check. X, I'm claiming, is what you get when you add together the first components. So what have we got? We've got in the first entry, we've clearly got x on the left. Here we've got 2x plus y over 3 times 1. So 2x plus y over 3. And then we've got plus minus 1 times this. So minus y minus x over 3. So if we now look at this, we've got 2/3 x minus minus x. So we've got a total of 1x. And the y terms, we've got y over 3 minus y over 3. So it does work. And you can check the second component, it will also work. So this particular combination allows us now, for any point xy in the Cartesian plane, we take 2x plus y over 3 lots of the first vector and add it to y minus x over 3 lots of the second vector, and that will give us this general point. So we can say that this set is indeed spanning. Now for linear independence, we follow a very similar method, lin in depth, question mark. But now what we want to do is solve alpha times the first one plus beta times the second one, minus 1, 2, equal to 0, 0. And remember, this will be linearly independent, provided the only solution is for both alpha and beta to be 0. So if we check this, the first coordinate will give us alpha minus beta is 0, so i.e. alpha equals beta. And then the second one tells us that alpha plus 2 beta has to be 0. But alpha, remember, is beta, so that's equivalent to 3 beta equals 0, which is equivalent to beta equals 0. And if beta equals 0, alpha equals beta, alpha is also 0. So we do indeed get linear independence, and so this set is also a valid basis. So what we're seeing here is that for a given vector space V, which here is the plane R2, we've actually got more than one possible basis. And this in general will be true, because we could just multiply this whole thing by some constant, or multiply each individual vector by a constant, and it would still work. It would still be possible to write any other thing as a combination of those two pieces. So rather than the basis itself being unique, that's why we tend to talk about the dimension of the vector space, which means the number of elements in the basis. Because here you can see both of them have 2 elements, and we have dimension 2, which is of course the dimension of 2D space, the xy plane. Now for our third example, let's consider the set, again, containing 2 vectors, but now let's have 1, 1 and -1, -1. So we know that we have the correct dimension, we have 2 elements, so it suggests it might work. However, we need this, again, to be spanning and linearly independent. So if we start by looking at spanning, if I'm given a point x, y, I need to find coefficients, let's call them a and b, such that this is true. So of course, a and b here we expect to be functions of x and y, as we've seen in these previous 2 examples. So if we follow our usual method, let's look at the first coordinate. We've got x is equal to a minus b, and then our second coordinate, what does that tell us? That tells us that y is equal to also a minus b. So this is a problem, because x and y, according to this, are going to be the same, but for any point in the xy plane, we are allowed to have x and y differing. So that's going to actually break these equations. So for example, if you had e.g. x was 1 and y was 0, this doesn't work, because then this would be 1, this would be 0. So this one tells you that a equals b. Plug it in the top, that tells you that 0 equals 1, which obviously is a very big contradiction. We never want to write that. In fact, I can't write that, I'm just going to rub it off. But it gives you a contradiction. It just feels far too wrong to write 0 equals 1. But that's what it would be suggesting. It's definitely a contradiction. So the spanning set idea doesn't work. They do not span the xy plane. And if you try to do linear independence, you can actually possibly immediately see this. The first vector is -1 times the second vector. They are multiples of one another. So you can rewrite one of them in terms of the others. So these are actually linearly dependent set of vectors, because we can rewrite one of them in terms of the other. So linearly dependent and not spanning. So definitely not a basis, because this particular set satisfies neither of the 2 conditions. So let's end by focusing on some examples around linear independence and linear dependence. So suppose I have the following set of vectors, so e.g. 1. So let's suppose I have 1, 1, 2, that's my first vector, 3, 1, 0, that's my second vector, and 1, 0, 1 as my third vector. And I'd like to know, is this set linearly independent? So as we've seen before with the slightly simpler 2 vectors, we start by forming the linear combination. So we consider a lots of the first one plus b lots of the second one plus c lots of the third one and that has to be equal to 0, which of course in this vector space, working in 3 coordinates, is 0, 0, 0. Now again, we want to solve this for a, b, and c, and we can conclude linearly independent if and only if the solution is a equals b equals c equals 0. So clearly that will work, but we want to see, is there another possible solution? So if we look at the first coordinate, what does that tell us? It tells us that a plus 3b plus c has to be 0. The second coordinate tells us a times 1, so a, plus b times 1 plus b, plus c times 0. So that has to be 0. And the third coordinate, what's that going to give us? It's going to give us 2a plus 0 times b, so that's 0, plus c is equal to 0. So I'm going to start by using the second one to say that tells me now that a is equal to minus b. And then for this one, I get that c is minus 2a, but a is minus b, so c is equal to 2b. So now I've got a and c in terms of b, so let's plug them in our first equation. So we're going to get minus b for the a plus 3b plus a c, which is plus another 2b, equals 0. So that gives us 4b is 0, so that tells us that b is 0. So if b is 0, I know that a is minus b, so this is now 0, and I know that c is 2b, so that's now 0. So we can see that the only solution to this equation, this linear combination of our 3 vectors, the only solution for them adding together to give me 0 is if all the coefficients are 0. So we can say, therefore, linearly independent. Now if I go back and change one entry in one of these vectors, so make a very slight modification to this problem, and replace this one now with a 5, then we can in fact show that this is now a linearly dependent set. And we would proceed in the same way, so I'll just use the red and sort of rub out our old working. So again, this is the only thing that's changed. That's become a 5 up here. And then our first equation now says 5a. And so what's going to happen is when we substitute, the other two, of course, haven't changed. When we substitute now, this is still true, but we don't know that it's 0. This is still true. Again, we don't know that that's 0. But we can now substitute for a being minus b into here, and what we're going to get is now minus 5b. So minus 5b plus 3b plus c, which is 2b, equals 0. So that just tells me that 0 equals 0, which again is something I don't like writing. So it doesn't give me any information. Point is, it gives me no information whatsoever. So what this is actually telling you is you can say, okay, so e.g. take b equals 1. So if I take b to be 1, then a is now minus 1, c is now 2. So if I plug those numbers in, let's check this works. So if I substitute in, a we've got as minus 1, I've said b was equal to 1, and then I've said c is equal to 2. Now let's check that this works. Our equations here suggest this should be a valid solution, and therefore we have a non-zero solution, i.e. linear dependence. So what have we got? We've got minus 5 plus 3 plus 2 is 0. That works. We've got minus 1 plus 0. That's also 0. And we've got minus 2 plus 0 plus 2 is also 0. So we do have a valid solution. We could, of course, pick any value for b, We could take that to be anything. I just picked 1 because it's quite straightforward. Key thing is we have a solution where not all of our coefficients are 0. Therefore, this time we have linear dependence. This set is now, with this very slight modification, linearly dependent. We'll finish with a final example of how to calculate a basis explicitly. Remember, we need to form a set of vectors which is both linearly independent and spans the whole vector space. So if we look at R3, our three-dimensional coordinate space, so 3 vectors, then one possible basis, so you could say R3 is the span of a linearly independent set, i.e. this is a basis, and we could take 1, 0, 0, 0, 1, 0, and 0, 0, 1. So the standard or canonical coordinate basis, exactly as we did in the plane, we can now do it for all of 3D space. However, we can also use this set, and that's why I left it at the top of the board, because we know this set is linearly independent. So we just need to check independent. We just need to check, is this set also spanning? So is it also spanning? Question mark. Okay, so we've seen how to do this for the previous case when we were working in the plane. So now we need a general point x, y, z needs to be equal to some combination of these 3 vectors at the top of the board. Of course, just for completeness, this is very easy for these 3. It's x lots of the first one, y lots of the second, and z lots of the third. Very straightforward to show that they are indeed spanning as well as being linearly independent. But it's a bit more work for these ones. So we need a lots of 1, 1, 2 plus b lots of 3, 1, 0 plus c lots of 1, 0, 1. And we need to solve this for a, b, and c, which of course will be functions of x, y, and z. So we're going to get very similar equations to we had before. So looking at the first coordinate, x is equal to a plus 3b plus c. Second coordinate tells us that y has to be equal to a plus b, and that's it. And then the third one tells us that z has to be equal to 2a, 0 lots of b plus c. Okay, so I'm going to arbitrarily rewrite this one as b equals y minus a. Okay, so suppose we have b is y minus a. Then what can I get from this one? I can get c is then equal to z minus 2a. So now if I plug both of these into the top equation, I should get an equation involving just a and x, y, z. Okay, so subbing those two into the top one, I'm going to get x is a plus 3 lots of b, so 3y minus 3a, and then plus a c, so plus z minus 2a. Okay, so what have we got there? We've got a minus another 5a, so minus 4a, take it across, we can say 4a is equal to 3y plus z minus x. So a, therefore, dividing 3 by 4. A is 3y plus z minus x over 4. So let's put a box around that. So now that we've got a, I can substitute this into this equation. So I can say b is therefore equal to y minus this. So I'm going to write that as 4y. So I can put it all over 4y minus 3y minus z plus x all over 4. So that's going to give me that b is in fact 4y minus 3y is y minus z plus x over 4. So now I've got b, and then finally I can hopefully figure out c is equal to z minus 2a. So c is, again, 4z, to put the whole thing over 4, minus 2 lots of this, so minus 6y minus 2z plus 2x. Okay, so that's going to simplify and tell me that c is equal to 2z minus 6y plus 2x all over 4. So I believe, and I'm sure those of you watching this video would love to check this, I believe this is A, this is B, and this is C. If you plug in those into this equation up here, you should find that the right-hand side here with these values of A, B, and C will indeed give you X, Y, Z, which does indeed show that this set is also spanning, and therefore this is also a basis of R3. As I mentioned before, do head over to ProPrep for even more exercises, as well as lecture videos covering all of the content from today's video. The best way to improve at maths is to practice, and with ProPrep you have a pretty much never-ending supply of questions. Just click the link in the video description to get your free 30-day trial. Thank you everyone for watching. Please do remember to subscribe to the channel if you've enjoyed the video, and I'll see you all very soon. Take care.